Once you have your parent function graphed, we can now apply transformations to that parent function. Again, we talked about the parent function using your 3 key points at the x values -1, 0, and 1. And then we need to remember what our transformations were from a few sections ago. Notice we start with the basic function f of x equals b to the x. B can be any number. It could be 3 to the x, 5 to the x, 10 to the x. But for now, we're going to leave it in general terms, b to the x. And if I add c to the function, plus c to the outside of the function, that shifts my whole function, parent function, up c units. But if I subtract c from the function, that shifts my parent function down c units. Notice on the next two functions, I'm adding c and subtracting c not to the function, but to x. When I add c to x, which is in the exponent, that's going to be a horizontal shift, and horizontal shifts are going to be left and right, opposite of your intuition, opposite of what you might think. Plus c, plus seems to think to the right, but actually it goes to the left c units, just like we talked about in the previous transformation section. X minus c, on the other hand, moves right c units. Again, all of these are moving from your key points. The reflections are a little bit different than what we talked about in the transformation sections before we kind of combined the reflections and the vertical stretch and compress. But I wanted to make sure that you saw that there was a clear distinction here, and we're going to add an extra piece of information that you haven't seen before. In the past, when we had a negative out in front of the function, that reflected over the x-axis. Or if you've transformed your vertex, it would just reflect over the vertex. But in this case, we're talking about just a negative. We're going to be reflecting over the x-axis. But if we have a negative on the x, now it's not in front of the function, it's just with the x. That's also a reflection, but in this case, it's going to be reflected over your y-axis. This one's new. We haven't seen this type before. We have talked about vertical stretch and compress before, and again, that was where we have a number multiplied out to the front of your function. If c was greater than 1, we had a stretch. And this is a vertical stretch. And if c was less than 1, but still greater than 0, we had a compress. Again, this is a vertical stretch and a vertical compress. But there is one thing to note on this. When I take c times b to the x, a lot of students will try to take that c and that b and multiply them together, raise it to the x. And that is not allowed. That is not true. For example, if I have 2 times 3 to the x, 2 times 3 to the x, a lot of students will say, oh, I know, 2 times 3, that's 6, right? 6 to the x. Well, that's a big no-no. You are not allowed to do that. The reason you're not allowed to do that is because of Pemdas, or order of operations. Order of operations says exponents come before multiply and divide. Exponents come first. So in this 2 times 3 to the x expression, 3 to the x exponent, this is going to have to be evaluated before you multiply by 2. So 3 to the x comes first before multiplication. Therefore, you can't take the 2 and the 3 and just multiply them. The 3 is a base, the 2 is a coefficient. You cannot multiply them and create a new base. If you still don't believe me, we can try plugging in a value. Let's say x is equal to, I don't know, 2, just because it's small enough to not have to do any calculator work. We have 2 times 3 to the 2, and we're comparing that to 6 to the 2. Using our Pemdas, our order of operations, 3 squared is 9, and 9 times 2 is 18. On the other hand, 6 squared is 36. These are not equal. Therefore, you cannot take the coefficient, in this case 2, and multiply it by my base, in this case 3. You are not allowed to multiply those two things and get a new base. You can continue to write it as 2 times 3 to the x. That's the only way you can do. Now, if you have more than one transformation, we're going to use order of operations or Pemdas to determine the order of the transformations. So let's take a look at this. I am given you one parent function, f of x equals 3 to the x. We're going to first sketch the parent function. After that, we're going to take each of the new functions, the red, green, blue, and purple functions, and translate their transformations from my parent function 3 to the x. Each one of these has a parent function 3 to the x inside the new function. If one of these functions said f of x is equal to 2 times 5 to the x, well, then you can't very well use this parent function. You'd have to create a new parent function for 5 to the x and do it. Now, we're not actually talking about that one in this particular step, but I needed you to understand that the reason these all go together is because they all have a common parent function 3 to the x. So let's look at the parent function. Now, I told you we could do this all from 3 points. Because my b is 3, I know my point at -1 is going to be 1 over the b, or 1/3. At 0 is always 1, and at 1 you always have 3. If you want to memorize the -1 comma 1 over b, always 0 comma 1, and 1 comma the b, and just plug the b in, that's great. If you don't, it's not so hard to just plug in -1 into the exponent. 3 to the -1 is 1/3. 3 to the 0 is 1, and 3 to the 1 is 3. So you don't necessarily have to memorize these. Either way, you're still going to get the same 3 points. And if you're really anxious, you can go ahead and plot another point. 3 to the 2 is 9, and then you have a little bit more accurate graph. I also should note that my horizontal asymptote is y equals 0. So I'll sketch the horizontal asymptote. It's a little low just because it's hard to see. So I'm going to go ahead and sketch it there. At 1, I got 1/3. 0 comma 1, 1 comma 3, and 2 comma 9. From that and my horizontal asymptote, I can sketch a very good graph. Next, I'd like to use this parent function to graph f sub 2 of x, which is equal to 3 to the x minus 5. This minus 5 is being subtracted to the x. When I subtract from the x, that's a horizontal shift, and that's a horizontal shift of right 5. Notice that my horizontal asymptote, if I shift my horizontal asymptote at the x-axis 5 units to the right, well, I'm still the horizontal asymptote at your x-axis. Shifting the x-axis right 5 doesn't really do anything to the horizontal asymptote. So I take each of my points, and I'm going to move each of them over 1, 2, 3, 4, 5, put a point. Next one, move it over 1, 2, 3, 4, 5. Move each of these values over 5 units using your horizontal asymptote, which didn't change in this case. Shifting left and right doesn't change your horizontal asymptote. Let's look at my green function, f sub 3 of x equals 3 to the x. Again, that's my parent function, but in this case I'm subtracting 4 to the function. When you subtract to the function, that's going to be shifting up or down. In this case, because it's minus, it's down 4. Now, my horizontal asymptote was the x-axis. If I shift my whole function, including the horizontal asymptote, down 4, then my x-axis asymptote will shift down 1, 2, 3, 4 to become a new horizontal asymptote at y equals -4. When you shift the points down, you also must shift down your asymptote. So I shift down each of these 4 units, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. And then I can sketch my green graph of 3 to the x minus 4. It does look like the black function has been shifted down 4 units. On f sub 4 of x equals the opposite of 3 to the x. Again, notice that we have my parent function. The only difference is that I am taking the opposite of the entire function, which is a reflection. It's a reflection over the x-axis. Well, my x-axis, or y equals 0, was my horizontal asymptote. If I reflect the x-axis over the x-axis, well, that really doesn't do much, it just stays the same. So my horizontal asymptote is still y equals 0. So I still have the same horizontal asymptote here. I'm just reflecting each of my points over the x-axis. So my first point was at negative 1, 1/3. When I reflect that over the x-axis, I get negative 1, negative 1/3. When I reflect 0, 1 over the x-axis, I get 0, negative 1. 1, 3 reflected gets me 1, negative 3. 2, 9 reflected gets me 2, negative 9. I am still approaching the horizontal asymptote at the x-axis. It's just I'm approaching it from the underside instead of the upper side. The blue function does look like the black function has been reflected over the x-axis. What we say we were going to do, you should at the end make sure that it looks like what you said you were going to do. On the last function, f sub 5 of x equals 2 times 3 to the x. Remember, 2 times 3 to the x does not equal 6 to the x. It just equals 2 times 3 to the x. We still have the 3 to the x function, which is the black function, but the times 2 tells me that I'm going to stretch by 2. And when I stretch this function by 2, my horizontal asymptote, when I stretch the x-axis, or y equals 0, notice I'm stretching away from the x-axis, so if I'm on the x-axis, my horizontal asymptote does not change. The height of the horizontal asymptote was 0, so when I double it, or vertically stretch it by 2, well, it doesn't change at all. Let's stretch each of the points by 2. At negative 1, 1/3, we're 1/3 high. Well, what's twice as high as 1/3? 2/3. At 0, 1, I'm 1 high. Well, what's twice as high as 1? 2. At 1, 3, I'm 3 high. Well, what's twice as high as 3? 6. And at 2, 9, I'm 9 high, and twice as high as 9 is 18, or clearly off my graph. Each one of these points should be vertically stretched twice as high as what it normally was on my parent function, the black function. So this should be looked, each point should be twice as high as stretched vertically, which it is. Take a look at all 4 of these transformations from the black parent function. Notice on all 4 of them, there's only one graph that changed your horizontal asymptote. All the other horizontal asymptotes stayed at the x-axis, which was the horizontal asymptote of your parent function. The only one that changed was the vertical shift of down 4. On the green function, we changed down 4. So I want you to note the horizontal asymptote stays the same unless you have a vertical shift. If your graph has a vertical shift, your new horizontal asymptote is just going to be y equals the vertical shift. But all other flexions, stretches, horizontal shifts will all keep your horizontal asymptote the same at y equals 0, or the x-axis.